What you have in front of you here is a simple bar magnet, right? I'm just waiting for this to stream up here. Right. So we have a simple bar magnet. A simple bar magnet has two poles, right? A north pole and a south pole. And around the bar magnet, there's something called a magnetic field. And the way for us to determine that magnetic field, we could use a simple plotting compass. All right. And you see that red part of the plotting compass? That red part gives us an idea of what direction the field pointed, right? So take a look at as I move the compass around, you recognize that the little red triangle pointing towards us. What that means is magnetic fields point towards us. Look at the next side. Magnetic fields point toward away from the north. You're seeing that? Look at the red triangle, it's pointing away from the north. And look, as I move the magnetic field, as I move the compass, look how the field line changing, right? I'll draw it for you just now. See that? It's pointing away from the north and it's going closer towards the south pole. You're seeing that? So the field lines look like that, right? That's what the field lines look like. Just follow the red triangle. So what it's saying is this. It's leaving the North Pole and it's going towards the South Pole. Okay? That's the way your field lines look. They leave the north and go towards the south. Are you okay with that? That's the way your magnetic field lines behave, right? Right, magnetic fields leave the north and go towards the south. If I decrease the strength of the magnetic field, why that's not working? Right? You'd recognize that you're not going to see the compass, not going to get any readings as you move further away. But if I make it stronger, look at the compass. The compass will respond in a particular way. That's okay. So what that's saying is that the further away you go from a magnet, the weaker it is. Okay. I'm gonna see if I could put two magnets together here. I will come back to electromagnets soon, right? All right. How do I come out of this now? What's wrong with this live anyway? All right. Watch this here. Right, let's check out this Java Lab simulation here. So we just go and take a look at what happens when two magnets come together, right? I threw this man coming late and I KFC and thinking here. Come early now, boy. Right, so watch this here. If you look here, we have a magnet, right? You all see the magnetic fields. If you have to draw it, just I'll let you draw this just now, right? That's how you draw your magnetic field. If I were to bring two magnets together now, a north and a south, what happens with north and south? North and south, the magnetic fields will interact, right? You're seeing that? The north going towards the south there. And well, you can't really see the south, but the south all here too, right? Not going towards south there. But there's an interaction of magnetic fields that will cause the magnets to attract, right? If I were to switch it around, okay, I can't switch it around. How do we now? You can just flip it over. Hold on, huh? Right, I get to flip it there. Wait, no, I flip it too much. Right, look at what happening there, right? You all recognize, look at the felines. You all recognize the felines not interacting, they're staying away from each other. You're saying that, so as I bring them, watch. Right, so no matter what I do, those felines not interacting. Right, they're not interacting at all. So that means that like poles will repel each other. Right? Like poles will repel each other. So no matter what I do, it's going to repel each other there. Right, so you do my favor here. Draw the felines here, please. Draw the felines around the north and you put in the arrows. Magnetic fields move from where to where? From north to south. So put the arrows going from north to south. Right? Draw that there, please. The green line, the green are the felines. Finish? So I'll bring in two of them together now. Draw the magnetic field lines for unlike poles. Unlike poles. Right? Draw the magnetic fields. Make sure you show it going from north to south. Yeah? Right? So on this diagram, you will see that unlike poles attract. Putting the direction, right? The direction is from north to south. Yeah, draw that for on-light poles. Draw those lines for on-light poles. Yeah, that's north and south. So they're on-light. And then you will draw light poles, right? And put the arrows on it. Then this diagram is the arrows, right? You're going from north to south. Okay, the light poles now. No? Yeah, now? Light poles now. Right, draw light poles now, not. And again, my diagram doesn't have the arrows, put in the arrows, right? Moving away from the north. All right, so take a small note now. A magnet, sorry, a simple bar magnet, a simple bar magnet has two poles on north and south. Has two poles. A simple bar magnet has two poles, a north and a south. Pulls up around these magnetic, around these magnetic poles. Around these magnetic poles are magnetic fields. Are magnetic fields. Are magnetic fields. Close up. Close up. The magnetic field is defined as the magnetic field is defined as the magnetic field is defined as the region around a magnet. Is defined as the region around a magnet where the region around the magnet where a magnetic force is experienced. A magnetic field is defined as the region around a magnet where a magnetic field, sorry, where magnetic force, sorry, where a magnetic force is experienced. Right, region around the magnetic field where a magnetic force is experienced. Where a magnetic force is experienced.
One day, yeah, why?
right? And full stop. The direction of the magnetic field is found by. The direction of the magnetic field is found by. The direction of the magnetic field the direction of the magnetic field is found by using a simple plotting compass. It's found by using a simple plotting compass. Right? Put in brackets, note that magnetic fields always go from the north to the south pole. Put in brackets, magnetic fields always go from north to the south. Repeat which part? Huh? It's plotting compass. Is it begin magnetism here? Right? Magnetic fields always go from north to south. I don't know why you're looking for. No. Magnetic field north to south here. Last year school year. Oh, what date is? School finishing on the 31st of March, last day in March. And crash course starting the 1st of April. Plenty subjects that are fit in 2 weeks. That's how to start first day. And first day is March, so physics. Right, what I was saying there. Right, and make a next full stop. Last thing. Light poles. Oh, I wrote this already on the diagram. Light poles repellent on light poles and chart, right? Okay, nice. Okay, so that's a little intro of magnetic fields. Right, what we're going to take a look at now is something called current carrying conductors and the magnetic fields around them. Okay, so next subheading, current carrying conductor. Current carrying conductor. So we're going to take a look now at current carrying conductors, right? There isn't really a simile. Anyway, I'll show you one is not the best, but all right. It's not the best thing in the world, but we could use it. Right? What it's showing you here, if you take a look at this circuit, right? Of course, the conduct, the wires, they're carrying current, right? Current going upwards. You'll see that? Let me just remind you. Here's your plus. Here is your positive and a negative terminal. That's okay? So current always goes from plus to minus, right? What the green arrow is showing you, the green arrow is showing you what direction the current moving in, right? You'll see that? You'll see the green arrow, right? Sorry, the green arrow is showing what direction the magnetic field is. So around the current carrying conductor, you have these little circles of magnetic field. You'll see that? So the green arrow is showing you the direction of the magnetic field. We could work that out using the first rule called Fleming's right hand grip rule. Right? So you're using your right hand and you're placing your thumb, right? Your thumb is in the direction of current. And your fingers in the direction of the magnetic field, right? So your fingers showing you that the magnetic field going in those little circles there. That's okay? Are you okay with that? So that's the first rule. It's called the right hand grip rule. Okay, it's called the right hand grip rule. So the right hand grip rule gives us an idea of how to find the magnetic field, right? You're okay with how to use it there, Emily? You all could use it there? Yeah. All right. So that's the way you use Fleming's left hand rule, right? Sorry, right hand rule. It's called the right hand grip rule. I'm just going to switch the current direction. So you will see, right? Look at the arrows change direction now, right? If I use Fleming's right hand rule, the thumb pointing downwards and the fingers pointing in whatever direction that is. Are you okay with that? Right. But really and truly, right? If I increase the strength of the current, you just see the field getting stronger, the arrows getting darker, right? So if you increase the strength of the current, the magnetic field will get stronger as well, right? So you see how it keeps changing direction there. All right. That is your Fleming's right hand rule, right? Let's take a small little note. Right, take a small little note, around a current carrying conductor, there is an associated magnetic field. There is an associated magnetic field. The direction of this magnetic field, the direction of this magnetic field the direction of the magnetic field is given by Fleming's right hand rule. Sorry, I keep saying, I mean, right hand grip rule. That's really Maxwell and Fleming who came up with it. Right? It's called the right hand grip rule. Right? Do a quick just sketch. The thumb is current direction. And the fingers are magnetic field direction. Right? Do a quick little sketch, right hand grip rule, right? That's the first rule in magnets. Right, so this is your first rule that we're going to look at. Right. You'll recognize it was kind of difficult to see the direction the magnetic field moving in. Yeah, you recognize that? So what they did is they drew the magnetic fields like this, right? They considered the current going into the paper and out of the paper, right? So here we have current out of the paper. So we're considering the wire, the conductor going into the paper, out of the paper, right? So if the current going out of the paper, I'll show you what to do. If the current into the paper, I'll show you what to do, right? So use your Fleming's right-hand rule and place your thumb going out of the paper. So place your thumb going out of the paper like this. Right? Out of the paper. So place your thumb coming out of your paper and your fingers will be pointing anti-clockwise. Yeah, anti-clockwise. So the magnetic field will be going anti-clockwise. Right? Yeah, right hand. Then take your right hand and place your thumb pointed inwards. And you will see that it's moving clockwise. Right? So it's much easier for us to say now, okay, well, magnetic field moving clockwise here and anti-clockwise here. Right? The red lines are the magnetic field. Yeah? Well, okay there? So the red lines are the magnetic field. Right, so just do your through that current going in and current going out. Nice. So you have a magnetic field, right? One more thing you have to point out is that whenever it moving in a anti-clockwise direction is a north pole, right? And whenever it moving in a clockwise direction is a south pole. All right, let's make a note of that now. So it's a north pole when the magnetic field moving anti-clockwise, and it's a south pole when it's moving clockwise. Okay with that? Right, so that's the way you find the magnetic field around a flat conductor, right? In case you all missed it online, I'm going to show you it here again. Watch on the board, right? If you have a magnetic field going in, current going into paper like this, and your fingers point the direction of the magnetic field. Okay, so current going in here, And then you use your right hand, point your thumb going inwards, and your fingers will point in a clockwise direction. Okay? Are you okay with that? Right? So that is the magnetic field around a straight conductor. Now we're going to make the conductor circular. Right? And let's see what will happen. So we have a circuit, right? We have a circuit connected to the circuit. Right? We follow the resistor, of course, so you can play the pulling out the wires, right? And we're going to put this in a circular way. Sorry. Right, circular, we're gonna put it on a piece of paper so we can draw it, right? This is paper, right? And here, the wire is going to come out here and go in there. That's okay? The wire going in, coming in. You'll see that? So the wire coming out the paper here and then going in the paper here. What direction of current flowing again? Current flow some which one to which one? Here's positive and here's negative. So the current going this way. Are you okay with that? So the current coming out here and it going in here. That's okay? Based on what you just learned, could you draw the magnetic field here and here? Right? As we just said, current coming out here and current going in here. Based on what we just said, see if we can draw that coming up, please. See if we can draw the field lines here and here, based on what you just learned. Huh? directions. Huh? Yeah. What I do? You went on the board and you get right. Good. Right. So that's the magnetic field around the circular conductor. Now we're going to take a look at a solenoid, right? Yeah, I'm going to spell it here for you. Right, so we're looking at a solenoid. What? All right, solenoid, right? So what's here? Right. Let's say instead of one coil, we have a few coils, right? Let's say we have a few coils looking like this. That there's a solenoid, right? So watch here. Current going up here and coming down here, right? That's okay. You all recognize that the current going in at the top and coming out at the bottom. You all seen that? In at the top. I don't know what I know how to say that, no? Right, so the current all what's here? All here going in, all here coming out. That's okay? Are you okay with that? Right. What's the symbol of it in again? Right? What is it? The X. So you don't have to draw it like this. Because the current always going in at the top and coming out at the bottom, here's what you can do. You can draw the X here and dot here. X here, dot here. X here, dot here. Right? So you can put X and dot to represent the same thing. Okay? X on the top, dots underneath. And I'll show you now how to figure out the magnetic field for a solenoid. Ready? So draw this and I want to show you how we going to work this out, right? Anybody remember what to do? What the rule is used? Same right hand rule. Right? So you're using Fleming's right hand, no, same right hand grip rule. Same right hand grip rule, but it's a little bit different, right? Right hand. Yeah. Right? Right. But the difference now, as opposed to here and the one before, the difference now is that the thumb points towards magnetic. Thumb points towards magnetic north. Right? And the fingers give the current direction. Right? The fingers give current direction. So watch it. Same right hand grip rule. Same right hand grip rule, right? We haven't reached the left hand and right hand rule as well. Yes. All we did is we changed the meaning of the fingers and thumb. Okay? So watch this here. So same right hand rule, current doing what here? Current going in and coming out. So watch your fingers. Right? The current going in at the top and coming out at the bottom. Right? So the current going in here, coming out. Make sure it's the right hand, right? And your thumb, trying to get the angle here for one line, right? right? And the thumb points towards magnetic north. All right, so here is north, and therefore here is south. Right? Watch it again. So it's going in, coming out, and the thumb towards the north. So if here is north, here is south. Once you figure out north and south, just do this. Magnetic fields leave the north, go into the south. Leave the north, go into the south. That's it. Okay? So remember, you're using the right hand grip rule, but in reverse, right? Copy it down.
Right? Or you can underscore equals school, but. I know you want to find it here. Nina, how do you produce the character? Who produces the character? Oh, we got a character from it's over there.
This is.
All together. Okay, so that is your first rules, right? Now here's what we're gonna do, right? Now we're gonna take a current carrying conductor and we're gonna put the current carrying conductor in a magnetic field. And we're going to learn the next rule, right? We're going to learn about the next rule here, but let's see if we can see it via simulation first. Huh? Where you get confused here? Are you sure? So where connection loss? All right, so let's take a look at hold on. I want to show you a little simulation here, right? Well, okay, online with the first two. Well, technically the first rule, but you're using them twice, right? Yeah, hi Prasad, you okay with us? Keshav? All right, so we're moving now and we're going to take a current carrying conductor and put it in a magnetic field, right? All right, something I'm playing in wrong. This is not allowed. All right. This is not the one I'm looking for. This is the one that's coming up for now, right? So watch this here. If you look here, you have your magnet right here. See the magnet? Right? You have the magnet and then there's a current flowing across AB. Right? It connected to a battery here and there's a current flowing across AB. You're seeing that? Yeah. See that? You're watching, yeah? Watch here, right? Hey, what is that, boy? All right, so if you look here, we are going to place the we are going to observe what is going to happen to the iron rod, right? So when you turn it on, wait, what happening there? It's not moving. No, that's just current. Hold on. Huh? Did I do something? Well, that was supposed to happen, right? But I don't know why it's not moving. So it's supposed to move. Hold on, let me just wait 2 minutes. All right, well, what's supposed to happen is that the rod's supposed to move downwards, right? All right, this simulation kind of lame. Hold on, eh? Just close the door for a minute, please. Sing a song. Right, just give me 1 second, right? I'm trying this. All right, we have a little problem here, not getting this simulation. I have to write down these things and remember. Keep going. All right, online. Y'all seeing that there? Yeah, y'all seen it? All right. It's not the best simulation, right? But here's kind of what happening here. Right. Here's what happening here, right? Here we have a right. Here we have a magnet. Most likely this is north and this is south. We have a magnet, and then you'll see that little piece of wire there. A small piece of wire in the middle there. Right. That wire. Mad lady. That's the wire that all right, sorry there. Right. So if you look here, we have a current carrying conductor in a magnetic field, right? The current carrying conductor is here in the magnetic field. If I were to allow it to move, watch here, you would recognize that it exerting a force and pushing it upwards. You're seeing that? Right? So what we're going to look at now is the rule that allows us to figure out the direction of that force. All right, so let's take a look at how to use this here, right? You head up current carrying conductor already, right? Next heading is current carrying conductor in a magnetic field. In a magnetic field, right? That's the last thing that we do. Current carrying conductor in a magnetic field. Current carrying conductor in a magnetic field. Right? So if you look here, you have a magnetic field, right? Going north to south, right? If I place a current carrying conductor in here, that current carrying conductor will experience a force, right, Jaden? Because here's why. This current carrying conductor has a magnetic field, and this north-south has a magnetic field. So it means that those two magnetic fields will interact and some kind of force will be experienced. Just like here. If I bring a north and a south, and the two of them have magnetic fields, so they will move into each other and attract. Same thing here. This has a magnetic field, this has a magnetic field, and they will interact. Okay? And they will interact, and we can work out the direction of the magnetic field by using Fleming's left-hand rule. Right? Left-hand rule looks like this. Right? You have your thumb, your first finger, and your middle finger, right? All the rest not important, right? So your thumb, your first finger, your middle finger. Your thumb gives the force direction, right? Your thumb gives the force. Your first finger gives the magnetic field. And your middle finger, right? So it looks something like this, right? Hold your hand like this. So you start with the thumb, 90 degrees to your thumb is your magnetic field, and then 90 degrees to the magnetic field is your current. So it ideally looks something like this. Right? This is your current direction, right? Right? I want to show you how to use it here. Ready? So watch this here. Say a magnetic field. Ready? Say a magnetic field is north to south. Say a magnetic field going downwards. So take your first finger, point it downwards. Right? This is current coming out or in. Dot means out. X means in. Right? So it's coming down like that. You'll see that magnetic field going down, current coming out. So if you use your left hand, your thumb should be pointing towards me. That's the direction of the force. Right? See it? Join in your book and try it. You always do it relative to your book, right? So the field must be your left hand. So your field going downwards, your current coming out, and your force will point in that direction. Okay? All right, so, oh wait, you'll write this already, okay. Supposed to give you a note before this. Supposed to give you a small note before this, right? Wait, I never sent a man, this is some handout, but I'm doing. Yeah, we began to a few. Magnetic field, north to south, current, coming out, force towards. Come on, try it fast. No, it off. Take it off. No, I mean off the live stream. Right? So north to south, current coming out, force this way. Right? So we're gonna do a few and we'll check it and see if we get it right online, okay? Take a small note before this, right? When a current carrying conductor, writing, when a current carrying conductor is placed in a magnetic field, when a current carrying conductor is placed in a magnetic field, comma, the magnetic fields, their magnetic fields interact. Their magnetic fields interact. Their magnetic fields interact. Right? Their magnetic fields interact. Full stop. As a result, a force is exerted. As a result, a force is exerted. As a result, a force is exerted on the conductor. As a result, a force is exerted on the conductor. Whose direction is given by Fleming's left-hand rule. Whose direction is given by Fleming's left-hand rule. Whose direction is given by Fleming's left-hand rule. Direction is given by Fleming's left-hand rule. Right, and you all drew it already, right? You all have it already? You all drew it already? All right. So let's try a couple and a round, right? So let's try this first one here. Well, this is number one. Let's try number two. Same thing. But magnetic field is north to south, right? But instead of north to south, I'm going to put an X in the middle. Use Fleming's left-hand rule and tell me what direction the force is now. Use Fleming's left-hand rule and see if you can figure out what direction. So let's feel like it's all the time, right? Your finger doesn't feel like it's all the time. Don't move your finger. The lyrics a little bit. It does well, not without. And next means what? Yes, boy. Yes. Book and then see where I go. Those who online message the direction, if it's to the right or to the left.
See?
Right, 1, 2, 3, right, yeah. So, Fleming's left hand rule, magnetic field going north to south, this current going inwards. So therefore, right, if you get in trouble, as some people then just rotate the hook, right? If you don't want to move. Current going in, magnetic field down, so the forces this way. Right, very good. Try the next one. North, south, X. Right, I'm bringing somebody on the board, right? I'm bringing anybody to do this one. You're Jaden. I will decide that. Right? Work out the seminar, please. Right, message up, down, left, or right. Up, down, left, or right, right? Bring Jaden. Right? Going down. Yeah. See? Right? Come. Well, you see? Come fast, all right. Yeah, I'll bring out some next kind of one, right? So watch this here. Right, Jaden going to show us the answer for number 3. Right? Current going in, correct? Magnetic field towards me. So the forces downwards. The answer is down. You should not up all the time. Right? The answer is down. Sorry. Right? So this here, well, watch here. This here is the principle of the transformer. Sorry, principle of the motor. Sorry about that. Yeah. So this here is what we're going to use to explain the motor. Yeah, they'll take off all the stuff. No, they're servicing 1, 2, so they'll finish that song. All right. So that's it there. Right? So next day we continue from right here. Fleming's left hand rule and going into motor.